Back to work. So our next set of lectures is from John Bologna, who will tell us about data analysis.
Okay, so I'm happy to be here lecturing to you guys. I'm going to talk about data analysis with a focus on the data that comes out of Monte Carlo simulations. Most of the stuff I'm going to talk about doesn't really depend on Monte Carlo simulations, so it's more general for those of you that don't work on Monte Carlo. I should also say that I'll start very basic. So if you're bored for the first half of this lecture or for the first lecture, don't feel bad. Hopefully it'll get more interesting. But I just feel like I should bring everyone up to speed, and there's certainly a lot of stuff I didn't know when I was sitting in your shoes, being exposed to data analysis as a graduate student. Okay, another thing I should warn you about, I tried to find some quotes by famous statisticians and physicists to spice up the slides here. I found one that I think aptly describes what you're about to experience by John Tukey. So I'm not a statistician, so this will be a very practice-oriented approach. Okay, so just very basically, I'll start by defining what a random variable is. It's a variable that can take values in any. There's no stick or anything. Okay, so I guess I could use that. All right, a random variable takes values in a set E. So this set E is completely arbitrary. But in addition to the set E, in order to fully define the random variable, we have to specify this thing, this function which I call P sub x, which is the probability density function for the random variable. This specifies with what probability you get each value in the set E. So formally, it's a map from the set E to 0, 1, which gives you the probability of getting the value in E. I'll distinguish between two different types of random variables. Discrete random variables, where this set E is countable, and continuous random variables where the set is not countable. Just some examples I came up with. If your random variable is the number of typos you find on the front page of the Irish Times on a given day, that's a discrete random variable. Similarly, the number of rainy days every week in Dublin is a very large random variable. Or could be coordinates of a random square on a chessboard. I put this in because this you could think of as maybe a tuple of two random variables, but you can still view that as a single random variable. Also, continuous random variables, if I had a random point in Rn or a distribution of all of your heights would be a continuous random variable, then might win that one. Or a value from my own research, in lattice QCD, each link on a four-dimensional space-time lattice is an element in the group SU3, which is parametrized by continuous numbers, so it's a continuous random variable. Okay, what do we want to know when we do Monte Carlo simulations? We want to know ensemble averages of functions of these random variables. So those are denoted by these brackets here, and they're just an integration over this set E, whatever the range of the random variable is. Then you evaluate the function of interest on each one of these elements of E and weight them by the probability distribution function. So just to be explicit here, I have the notation if it's a discrete or continuous random variable different. But in practice, this doesn't really matter. In fact, for the rest of these lectures, I'm going to just assume that we're dealing with continuous random variables. You can always recover a discrete random variable from a continuous random variable by assuming this thing is just a superposition of delta functions with the values that the discrete random variable can take. Okay, I should stress here that all of these probability density functions have to be normalized so that the ensemble average of 1 is equal to 1. Okay, everyone okay so far? This is all super basic. Yeah. Okay. All right, slightly more complicated. You can have functions of multiple random variables given by the integral over this product space. But note how I write the distribution function here as a joint distribution function over all n random variables. That's the most general form you can have if you're considering a function of n random variables. This joint probability distribution function doesn't necessarily factorize. What I mean by factorize, if I can write this joint distribution function as a product of all of, well, in a product form where the dependence on each of the random variables is explicit, then I'll call these random variables independent. Otherwise, I'll call them correlated. So if this joint PDF is non-trivial, then these random variables are correlated. I guess while I'm thinking of it, some other important definitions that I didn't write down here. In analogy with the PDF, we also have the cumulative distribution function. Which is defined as the integral from -infinity to x s of the PDF. So here I'm considering a random variable defined on a set of real numbers. So anyway, these CDFs will come into play later, so I'll just define them now. Okay, so this form for the joint PDF of a bunch of random variables implies that they're independent, otherwise they're correlated. All right. While it's important to talk about these functions of random variables because those are the observables that we'll be interested in when we do Monte Carlo simulations, the distinction between random variables and functions of random variables is pretty arbitrary because a function of a random variable is itself another random variable. So if I just decide to define f of capital X as capital Y, I can write this ensemble average in two different ways. The reason I make this distinction is because typically when you do a Monte Carlo simulation, you measure a bunch of things directly when you're performing the simulation. Those I will call primary observables. But often you're interested in other quantities in addition to the things that you measured directly from the simulation. Those I will call secondary observables. But as we see up here, there's really no difference between a primary and a secondary observable. It's just operational, if you like. You're given these and you have to infer information about some secondary observables. For that reason, it doesn't really make sense to talk about tertiary observables or anything like that. You can view these as primary observables when you put them into another function. Okay, these are all basically just definitions. Some more definitions. Important characteristics of random variables. Here are two. There are the moments. These are properties of the PDFs of the particular random variables. The moments are just ensemble averages of these powers of the random variable. The first moment you guys probably already all know, it's called the mean. Pretty standard. In addition to moments, there are also cumulants, which are given by this equation here. One cumulant, which you guys might also know, is the variance, which is the second cumulant. You can see here that the first cumulant is identical to the mean, but the second cumulant is this combination right here, the variance. Just generally, this, if you have a PDF which looks like this, the variance kind of gives you a measure of the width of the PDF. Anyone know special names for the higher cumulants? Like kappa 3? Kappa skewness, yes. Kappa, anyone know anyone else? Kappa 4? Not quite. Intercumulants are something else. I think kappa 4 is called the kurtosis. Anyway, these are just questions you might ask if you're given a random variable. I'm guessing that's kurtosis, and I'm guessing you spell it that way. Looks Greek. Maybe it's Greek. Anyone Greek? Speak Greek?
Yeah, it's really that.
Okay, yeah, all right, good. All right, right. Okay, so everyone's fine so far, or questions? Okay. So just some examples of random variables that everyone probably knows. This one, the Gaussian random variable. You have to put this prefactor in front so that it's normalized properly. But I can never remember it. So I will entrust to you guys a handy mnemonic to remember not only that prefactor that you need, but also all of the moments of the Gaussian random variable. So the only thing you have to remember when you're dealing with exponential integrals of this kind is that the following integral ax squared. Anyone know this one by off the top of their head? Root pi over a, exactly. This is all you need to remember. Of course, that fixes the prefactor there. You can see that that prefactor is just root pi over a. And all of the even moments for example, well, first, it's easy to see that given that distribution right there, the mean would be mu. All you have to do is shift the integration variable, and then based on the normality of the, yeah, anyway, it's easy to see. But this one's maybe more non-trivial. Anyone know a quick way of doing this integral? Yeah.
Introducing that constant derivative for a. And, yeah.
Exactly. So I can write this as minus dA of the integral minus infinity. I'll just put it on the second line. Minus dA minus infinity. Yeah, so given that, put it in here, and then you get the requisite moments. In America, we call this the Feynman trick, but I'm not sure if that's international or just our own bias. Okay, that's the Gaussian random variable. It's widely useful for all sorts of different things. The exponential random variable, for example, might be used in the amount of a radioactive sample that's present after a particular time interval. This is considerably easier to manipulate. And then just for completeness, I give you the Cauchy random variable, which is relevant for the distribution of atomic line shapes, among other things. The reason I bring up this is that here I've given you these two characteristics. I've mentioned the mean and the second moment. But those don't necessarily have to be defined. This Cauchy random variable here is fine as a random variable. It's positive definite. It's normalizable. If I integrate that thing from -infinity to infinity, it's equal to 1. That's fine. But the mean and the variance don't exist. Once I put an x in the numerator and integrate over that, that integral diverges. Similarly, if I try to do the same with the variance. In fact, all the moments and all the cumulants diverge for the Cauchy random variable. But it's still a fine random variable to talk about. It just doesn't have any moments or cumulants. So, interesting example there. Okay, any questions about examples of these silly examples of continuous random variables? All right, just for fun, we can talk about some common discrete random variables as well. If I have a process that can either succeed and give me a 1, or fail and give me a 0, and I consider this random variable x, and I assign probabilities to these two outcomes, say p, 1 minus p. This is called a Bernoulli random variable. And these first two examples I gave of discrete random variables are related to this Bernoulli random variable. The binomial distribution up there, anyone know how that's related to the Bernoulli?
N Bernoulli drives. You do N Bernoulli drives, then the distribution will come to the Bernoulli.
Exactly. If I ask for the number of successes in n trials, that number is distributed according to the binomial random variable. You can see here that binomial coefficient naturally appears because it doesn't matter in which order the successes or failures occur in the n trials. So that's why I have this multiplier due to the Bernoulli coefficient, and then I have, k successes have to happen, so I have p to the k, and then n minus k failures have to happen, so I have 1 minus p to the n minus k. You can easily calculate the mean and the variance of the binomial distribution as well. What about this guy? How's this guy related to the Bernoulli?
At least one success.
At least one success?
At most one success.
At most one success.
One mean.
Exactly. So this gives you the number of trials you have to perform in order to get one success. You can see there's no combinatorial factor in front, and I have to have my first k minus 1 trials fail, and then my kth trial succeed in order to get k trials before my first success. Okay, you guys are pretty good with this. What about this bottom one? How do I get a Poisson distributed random variable? Sure. That's one way of thinking of it. It's from the exponential distribution. I'm not sure how to derive the Poisson from the exponential distribution. Yeah, I think that's probably related to your relation of the Poisson variable to an exponential. If you have a process where the times between occurrences of a process are exponential distributed, then the number of occurrences in a particular interval is Poisson distributed. So you're right, it is related to the exponential in that sense. It's also related to the binomial. You can take the following limit of the binomial distribution to obtain the Poisson. So if I take the binomial has two parameters, n and p. And if I take the limit as n goes to infinity and p goes to 0, but I keep the product n times p fixed and equal to lambda, then I get the Poisson with parameter lambda. So this kind of gives you an intuitive feel for what the Poisson means. If I have some sort of, Bernoulli type process, but it keeps happening over and over again, continuously, that's taking n to infinity, but the probability of a particular success goes to 0, that's taking p to 0, then I recover this Poisson process, where the product of n times p is fixed to be lambda. So this was one of these great 19th century gambling mathematicians, Poisson, and I think the first ever Poisson random variable was the, again, this is where I stole the first slide, the number of typos on the front page of Le Mans. If you consider the number of typos in a fixed time interval, that number will be Poisson distributed. Okay, this is just for fun. These are just common random variables that pretty much everyone should know, so I throw them at you guys. Good. All right. We've looked at types of random variables. We've looked at ensemble averages, and given, and when we've looked at a random variable, we've defined it according to its probability distribution function. And then given this PDF or PMF, you can calculate anything you want. You can calculate all the probabilities of outcomes for experiments based on these random variables. But in fact, that's not the question we would like to ask. So the general philosophy of what we've been doing so far is, given the underlying distribution, what are the results of some Monte Carlo calculation, right? If I have this PDF, I can calculate what I expect to see. But that's never what we do, right? We do an experiment, we do a calculation, and then we want to learn properties about the underlying distribution. So this is the difference between probability and statistics. To paraphrase this famous Italian statistician Bruno Di Finetti, probability does not exist. You have to do statistics. But unfortunately, statistics is much more of a black art, which is evidenced by this English statistician's quote. Statisticians, like artists, have the bad habit of falling in love with their models. You have to make a model in order to do statistics of the underlying distribution of the data. That model might not be correct. You have to put assumptions into that model, and then using that model, you have to try to infer things from the data about the distribution that you want to know. So that's where we're going next. I actually don't have a, okay, good. All right, so we're moving from probability to statistics. One useful result in constructing these models of the underlying data set is the central limit theorem, which we'll talk about right now. So if I have n random variables, now these should be viewed as n trials of the same experiment. A fancy statistics way of saying that is that these are independent and identically distributed. So we talked about independence, and they all have the same distribution. Furthermore, the distribution that they all share has a finite mean and a finite variance. That's crucial for this to work. If this holds, then I know that the distribution of this quantity, the sample mean, tends to a Gaussian in the limit that n goes to infinity. This is very, very important. So whatever distribution you start with for the underlying x's, if I calculate the sample mean and take n large, I get a Gaussian. This is tremendously powerful. And we're not going to prove it here. There are varying degrees of proof depending on whether you read statistics or physics texts. But I'll let you do that on your own. But before we move on, we'll look at some examples of the central limit theorem. This first example concerns these Bernoulli random variables that we were talking about earlier. We already know that the sum of n Bernoulli variables is distributed according to the binomial distribution, right? So this gives us some information as to how the sample means for a Bernoulli random variable would be distributed. Of course, instead of putting a k here, as we had a few slides ago when we talked about the binomial distribution, if I want to talk about the sample mean, I have to divide by n. So if I have n equals 10, instead of the integers 1 to 10, this random variable will have all of those integers divided by 10 as its possible values. So in fact, it's quite easy to show by just brute force calculation that if you take the limit as n goes to infinity of this distribution, you get a Gaussian. And not only that, you get a Gaussian with mean p and variance p times 2 divided by n. So you can see that this satisfies the central limit theorem, where you're supposed to have the mean of the resultant Gaussian equal to the mean of the original distribution, and you're supposed to have the width of the resultant Gaussian equal to the variance of the original distribution divided by square root of n. So this is a handy test, and you can just show it with a bit of algebra. So I'll leave this for you guys as an exercise. Just apply Stirling's formula to this factorial and you'll get it with a bit of algebra. But it's fun, and you can really see not only that this thing works, but you also get a handle on the size of the correction to the central limit. Okay, I guess I should emphasize the fact that the width of this Gaussian decreases with square root of n. This is in a sense why we do more measurements when we do an experiment. If I take this sample mean over more and more measurements, then that sample mean becomes more and more sharply peaked around the true mean. And it becomes more and more accurate as I take n to infinity. Okay, so this is a handy exercise to have fun with for you guys. I'll do the cheap trick and prove it by graphing. That's not okay. You should do it using actual calculation. But you can see how this works. If I take even some fairly small values of n, and I look at this binomial PDF rescaled so that they all have the same height, as a function of k over n, you can see the width shrink, and by the time we get to n equals 20, we're basically at a Gaussian. So this central limit theorem gets saturated quite quickly in n. So even after 20 trials, it's behaving like infinity. So that's nice to see. If I fit that thing to a Gaussian, I get exactly the correct answer. It's very small. All right, so this has to work. You guys should just show it. Okay. All right. A warning about the central limit theorem. It's super powerful, but before we go on, I just want to emphasize that it's only applicable if the mean and the variance are finite. So here I've actually plotted these sample means for a Cauchy random variable. Remember, that's the one where none of the moments exist. None of the moments converge. So again, I just used the C++11 random library to generate this. It's pretty easy, but I'm sure Python or Mathematica or anything like that allows you to generate Cauchy random variables. This is a neat thing to play around with. Anyway, as you track this sample mean for n large, you see that there's no hint that it's converging. It shouldn't converge. The central limit theorem doesn't apply. So it just jumps all around. But if you do the same thing with a random variable where the central limit theorem is applicable, like this exponential random variable with lambda equals 1, you can see that the picture is completely different and it does converge. Is it converging to the right answer? What would you expect for the mean of a exponential random variable with lambda equals 1? 1, exactly, right? But this thing looks like it's heading for 1.05. Is my code wrong? What's up with this? Should I go back to the drawing board, check my scripts, complain to the C++ standards committee?
The quality of the random numbers was not very good.
Maybe the quality of the random numbers wasn't very good. So maybe, yeah, maybe my RNG was wrong. Any other explanations? Well, what would you expect if I had n equals 1,000 for the width of the distribution of the sample mean? So remember, the thing's distributed as a Gaussian with mean equal to the true mean, so it's an unbiased estimator. And then the width of the Gaussian is the variance divided by square root n. So what's the variance of the exponential distribution with parameter lambda? I think it's also lambda or 1 over lambda, but that doesn't matter, it's just equal to 1. But if I then look at the denominator there, 1 over square root of 1,000, it's actually not that small. I think this is something like 1 over 30 or 40 or something like that. So maybe not so surprising that you see deviations of 5% or so. So the data might not be wrong at all. This just might be because we only took 1,000 trials. And in fact, that is what's happening. If I take 10,000 trials, I then expect this to be more like 1 over 100, so 1%. And I get convergence right to the correct answer. So again, whenever you're looking at some data, it very well may be a bug, but you should also make sure you have in your mind a good expectation of what the data should look like. There was this quote by this famous statistician Fisher, calling in a statistician after the experiment has been performed is like calling in a doctor to do a post-mortem. He can tell what the experiment died of. Anyway, it's always good to keep in mind what you expect. Just for completeness, if I run the Cauchy guy for 10,000 trials, it's still jumping all around. Okay, right. So to finish up our discussion of the central limit theorem, why is the central limit theorem so useful? Well, in colloquial terms, it's this fact that we know that the distribution of the sample means gets narrower and narrower, and we can quantify exactly what that distribution is. So, for example, we can consider the probability that the sample mean differs from the true mean, and by how much does it differ? So if I want to consider the probability that the sample mean differs from the true mean by at least the standard deviation divided by square root of n, this is easy. It's just an integral of the normal distribution, a definite integral of the normal distribution, and that's about 68%. That the difference is less than the standard deviation divided by square root of n. Similarly, if I widen this interval to twice that, then the chances that I'm inside that interval are 95%. And if I widen this interval to 3 times that, then the chances are something like less than 1% that I'd be outside the interval. So these intervals are special. These units of the standard deviation. So all I'm doing here is, if I consider the sample mean minus the true mean multiplied by square root of n divided by sigma, then this thing should be distributed with a Gaussian centered at 0 with width equal to unity. I'm just considering these intervals here. So this is 68%. If I make this twice as big, then it's 95%, and 3 times as big. This is all symmetric. And it's 98%. Anyway, these are great because you can quantify exactly how likely it is that the sample mean differs from the true mean by these particular intervals. The general term for these things is called confidence intervals. So the confidence interval, which I've denoted by A, comes with a confidence level called alpha. So if I say the difference of the sample mean from the true mean is smaller than A, I have to pair that with a corresponding confidence level. So if you go back here, the difference that the sample mean and the true mean is less than this 1 sigma bound, well, that's confidence level 68%. If you're given a random variable where you think the central limit theorem applies, you can calculate these confidence intervals yourself by using the error function, which is the definite integral of this Gaussian function. So again, C++ comes with this. Python, Mathematica, this is handy for calculating confidence intervals. Okay, so make sure I don't run over here. All right, just to summarize the whole procedure here, which you guys have been knowingly or unknowingly following for your entire scientific careers. If you want to quote a point estimate for some quantity you've estimated from Monte Carlo, you calculate the sample mean. You calculate the sample variance, and then you quote the sample mean plus or minus the square root of the sample variance divided by n as your point estimate. So these are 1 sigma errors. But again, it pays to keep in mind that the probability that the sample mean and the true mean differ by this much is 68%, which isn't as ironclad as you might think. So if you're worried your code is wrong because there's a 1 sigma deviation or a 2 sigma deviation of this thing with respect to what you think the true mean is, maybe that's not so significant. This only means that there's a 68% chance that this thing is close within that interval of the true mean. Okay. Right. Yeah. So that was our first foray into statistics. We made a model of the underlying data, namely we assumed that it was in this Gaussian regime so we could apply the CLT, and then we used the data to infer things about the underlying distribution. We can formalize this idea of how certain we are about some statement we make by defining what's called a test statistic. A test statistic first requires a hypothesis. The hypothesis one constructs is usually called the null hypothesis, and then you calculate a statistic to quantify the deviation of the data from your null hypothesis. Using that test statistic, you then calculate a p-value, which represents the probability that you see a test statistic that's at least as deviant as the one you observed. So small p-values, meaning that the probability of observing such a test statistic is small, refute the null hypothesis. So a small p-value means that your assumption was wrong, but how small is actually quite subjective. The general rule of thumb is that if it's much smaller than 5%, then you've refuted the null hypothesis. If it's much larger than 5%, then you have not refuted the null hypothesis. If it's around 5%, you should probably do the experiment over again with more data. And then one more thing, it's unlikely that it'll be extremely close to 1, something like 0.99. That seems unlikely that you get a test statistic so close to the null hypothesis. So seeing something like this might also indicate a problem with your analysis. The analogy I always like to give for this is if you had someone, like a graduate student, if you instructed them to go off and flip a coin 10,000 times and report the number of heads and tails, and then the graduate student came back to you and said, yep, done, got it done, I got 5,000 heads and 5,000 tails. You'd be like, really? That seems weird. That's the equivalence of getting a test statistic so close to the null hypothesis. Anyway, just as an example, which I can let you guys work on for a few minutes. These lectures are online and the answer to this exercise is on the next slide. So I'm working on the honor system here that you guys won't click ahead. So anyway, maybe I'll give you guys a few minutes to think about this and then we can talk about how you'd solve it. If I had a random variable and my null hypothesis was the mean of the random variable is equal to 10, and then I got this data, what kind of p-value does this correspond to? Is this a really small p-value? Does it refute my null hypothesis? Is it a larger p-value? Does it not refute my null hypothesis? How would I even calculate this? Where would we start? That's right. So the central limit theorem in a nutshell is that this quantity, square root of n, times the absolute value of the sample mean minus the true mean divided by sigma is Gaussian distributed with mean 0 and width 1. So let's calculate this thing. The deviation of the sample mean from the true mean multiplied by this standard deviation. That's easy enough. I'll make you guys do it. You get something like 0.29 when you do that. That's just plug it into a calculator, it's fine. Great, now we have to turn that into a p-value. So what's the probability that I get a difference at least as large as this one. Well, I have to integrate the normal distribution. The normal distribution centered at 0 is symmetric, so instead of going from minus 0.29 to plus 0.29, I can just multiply by 2 and then do the one on the right-hand side of 0. If I know that the Gaussian distribution is normalized, I can rewrite this as 1 minus the flipped integration limits. Oops. Yeah, that's not quite right. Yeah, that should be 0 to, yeah, sorry, I'll correct that. But anyway, you can then interpret that in terms of this error function, and you get a p-value that's pretty reasonable. So these numbers I just made up seem to be reasonably distributed with a mean of 10. But it's maybe, it's fine. Okay, so that's a very simple example of how to calculate a p-value. Okay, I'll just start this now. We'll continue it next time. But that was an example of a very simple hypothesis, one that provided a value for the mean. What about more complicated null hypotheses? What if I have a null hypothesis that specifies the entire PDF of a random variable? There are two techniques to address the p-values in this case. If the random variable is discrete, we have the chi-squared test, and if the random variable is continuous, we have this KS test, the Kolmogorov-Smirnov test. First, let's talk about the chi-squared test, the one that's applicable for discrete random variables. So, null hypothesis for a discrete random variable provides us with this probability mass function P of k, and then the experiment is performed, and we get the data, which is the number of outcomes for each of the possible values of the random variable. So you can think of this as a dice roll, and I tally up the number of 1s, number of 2s, number of 3s, and so on. After I do that, I then construct this test statistic, chi-squared, which is the expected number of each outcome minus the observed number of each outcome squared divided by the expected number. You can convince yourself with a bit of algebra that this thing should be distributed according to the chi-squared distribution with n-1 degrees of freedom. I've shown you here the PDF and the CDF for the chi-squared distribution, which allows you to calculate the p-value. So given the data, you calculate this chi-squared test statistic, use this cumulative distribution function, and a calculation similar to the one we did for the Gaussian random variable to obtain a p-value. Anyone know where this funny chi-squared distribution comes from?
Do the sphere in n space.
Well, I don't know about that one. Really?
Yeah, I think so. It's,
Okay. I just know it as the sum of the squares of however many Gaussian distributed random variables. So this makes sense given our discussion of the central limit theorem. This deviation without the square should be Gaussian distributed. So you have the sum of the square deviations, where each of the deviations is a Gaussian distributed random variable. That results in this chi-square distributed guy. Why n-1?
Isn't it about the constraint that the mean already gives a constraint to the system, so you actually reduce the number of risk median?
You're exactly right. I know that I'm doing small n total trials. So I do have a constraint on the system that the sum over capital N1 to capital N little n has to equal little n. So in fact, specifying n-1 of these guys is enough to specify the last one. So this thing is really distributed according to the chi-squared distribution with n-1 degrees of freedom. And then I've got another little example here for you guys. Just for fun, we'll do a 5-sided die. Maybe that's useful for Dungeons and Dragons or something. And my null hypothesis is that the die is fair, so that P of K for each of the different Ks equals 0.2, 20%. And then I roll the dice 50 times, or I foist it off on a graduate student, and I get these numbers for each of the different outcomes, 1, 2, 3, 4, and 5. So how would I obtain a p-value that quantifies whether or not this was a fair die? Well, I just calculate the chi-squared on the previous slide. All those n times p's are the same, and I get 12.8. And then I would integrate from 12.8 to infinity the chi-squared distribution with 4 degrees of freedom, which is just given by that equation there. This is a special function that's called the incomplete gamma function. It sometimes differs in different texts on whether or not it has this normalization in front, but it's also implemented in most numerical software packages, so you can use it to estimate the p-value from a chi-squared. And if I do that, evaluate this guy, I get something like 1%. So this most likely is not a fair die. Okay, that's maybe a good place to stop. We can talk about the KS test next time, which I think is tomorrow. Any final questions about anything? No? Okay, great.
Well,